Okay, so moving beyond chapter 6, I should say, where we just had planets in an orbit and they take a long time and things like that. In physics, we often deal with things like wheels. We're going to get to rolling and rolling without slipping, true circular motion this time. Something that's an actual circle or cylinder rolls down an incline ultimately, or through a loop or whatever. Or we have a piece of an engine or a machine that just spins over and over in its same spot. So it's not really appropriate to address that with orbits. We might also have some funny shaped object that's really not a circle, but we're tracking a part of it that moves in a circle. There's something stuck in a centrifuge or something keeps moving. I kind of don't like that first picture up there. I feel compelled to use it. Remember, like we've been doing in chapter 9, in math class, you would measure an angle. If something moves around an origin, you would measure a positive angle, theta, right there. Okay, well, in physics, the biggest angle we can go to and cycle around is 360 degrees, of course, but that's also once around the circumference. So physicists thought, I don't want to count in 360. There's insane reasons for that, using 60 and 60. We're just counting on our fingers. That's silly. Once around a perfect circle is 2 pi, 2 pi r circumference. Oh. And if an angle is just a fraction of a rotation, then I'd rather have a measurement that's a fraction of the circumference. So if we take the circumference 2 pi r and divide by the radius of the circle, right? That's the point of an angle. Is an angle is just the difference in degrees. It matches any size, right? Any size triangle or any size shape that has the same angle is congruent, they would say in geometry. So that comes out to something called radians. Have you heard of radians before in trig class? Oh, thank goodness. It's just a substitute for 360 degrees. 2 pi radians is once around in radian measure, just like 360 degrees. That represents one revolution. Okay, just like 2 pi r is once around the circumference of a circle. Okay, any questions so far? Well, if we're measuring angles, you could even think of this as angular position. We call theta. We can have angular velocity, which is just the change in position over change in time. Sound familiar? The only thing that's different is the symbol is not familiar. I'll zoom in on these in just a second. Okay, but there's angular velocity. There's even rotational inertia, because inertia doesn't have an angle itself. It's just the mass, or it's rather now it's distributed mass. Okay, so we'll just zoom in here. Oh, that went terrible. Why? If I could learn my technology. Okay. Alright. It's very helpful for you to write them out. I should just grab that thing. Okay. By the bored looks on your faces, I can tell. So we'll have a displacement before, and now we have angular displacement in radians. We would have velocity, which is distance over time. Well, now we have radians over time, and we call that little omega, or W, or Calvin likes to say W in rad per second. If that in turn changes, we have change in W over time. We call that alpha because it's like acceleration, but it's radians per second squared. It's actually just the same as chapter 2, except meters has been exchanged for radians because we're forcing ourselves to be constrained to move in a circle. We still could get the linear acceleration along a circle, okay? But hey, just like on that circle, I kind of breezed over that. If we have an arc length, so not 2 pi circumference all the way around, just an arc, we call that s. Well, if you divide the arc by the radius, that should have been in geometry class, then you get the angle in radians. Okay, if you divide the actual speed, here's the conversions in blue. If you divide the linear speed by the radius, v over r actually equals w. Okay, it's delta s because you have to be along a curve unless it's a really giant curve. Delta s over r equals theta. Well, I ran out of room. Let's move it up there. In radians. Okay, and if you actually have a linear acceleration, we call that t for tangent, as in along the circle tangent. Divide that by r and you get this alpha. So they're not that alien. We're just exchanging meters for radians because we're moving in a circle all the time. We're working up over many days. We'll get to rolling afterwards. So after break, we got to get to rolling, where something is both spinning around its own axis and it's rolling. And those ratios don't necessarily match. You can roll and slip, and you can roll without slipping. And I think if you have any driving experience, rolling without slipping is much better. Well, and then your tangent velocity has to equal your velocity along the ground also. If you roll without slipping, the rate at which the wheel applies more of its circumference to the ground is actually the rate that it moves along the ground. Then we can do some fun problems. Maybe a lab. Any questions? Well, okay, the first lesson in chapter 10 is just translate that. Can you do it? Okay. Oh, don't forget, we are moving in a circle, so we still have our v squared over r. The zoom in should work better this time. There we go. A little bit better. A little bit better. Okay. Okay. You might have heard of frequency. It's just 1 over the time period. Yeah. We breathe. This I know was in, because I can't resist, was in chapter 6. The time for 1 revolution. Okay. If I have omega, or wa, in radians per second, how can I translate it to revolutions per minute? Okay, I need to do, that really is the same quantity, but I need to switch radians to revolutions. So I do like a stoichiometry, except it's just units. Okay, I have 1 rev is 2 pi radians. So I divide by 2 pi. And then I have per minute instead of per second. Well, I have to multiply by 60 seconds to get rid of seconds over 1 minute. So it's 60 over 2 pi or 30 over pi. It's really easy, actually, to transfer back and forth, but it's hard to remember. That's why it belongs in your notes. It's hard to remember that that's the conversion from radians per second. If you have revolutions per minute, you can multiply by pi over 60. Oh, it's about a factor of 20. Okay. Any questions? We'll get to some examples. Try not to go too long. Okay. Probably make it. Okay. All right. That's on your equation sheet, isn't it? That came. Oh, it was so big now. It had to come side by side. But that's why it's so big, because you can just any of these angular constants or angular quantities, They work exactly the same as the old stuff from chapter 2. Exactly, exactly. Okay, you just have to remember that these funny Greek letters, this is Greek omega, Greek theta, Greek alpha. The Greek letters are going in a circle with no unit of distance. It's all angles. Okay. But you have an average velocity, that distance the angle moves, the average velocity times time, all the same stuff. Okay. Rotational kinematics, rotational dynamics. Any questions? Okay, we're going to connect that, maybe not tomorrow. It's time for a break. But we're going to connect that when we get back right away to, we've just been doing torques in chapter 9, and unbalanced torque causes an angular acceleration. Okay, things will start to spin or stop spinning. Okay, but for now, let's just do some quick computation examples. If a sprinter runs around a circular track at 10 meters per second, the radius is 20 meters. This is like an indoor track, almost circular. Calculate her angular velocity. Can you do it in your head real fast? Or are you writing the example? Okay. Maybe pause for a minute. Alright, so let's try it. Radians per second. Okay, W is just V over R. So seriously, 10 meters per second. It has to be the radius of the circle you're going in over 20 meters is 0.5. Did I have 3 sig figs? I did. Radians per second. That's it. Super easy. Okay. What's 0.5 radians in RPM? Revolutions per minute. That should say rad over 1 second. Okay. What did I say? It was 30 over pi? Oh yeah. It's 2 pi radians. Cancels that out. That's 1 revolution. And 60 seconds per minute. Okay. So, yep, 30, half of 30, 15 over pi. You can get what exactly that is. But about 5 RPM. At 10 meters per second, that's a short track, but over a minute, 10 meters per second. Oh man. Does that make sense? The radius, so it's about a 120 meter track if it's a perfect circle. 2 pi, yep. And at 10 meters per second, 12 seconds around, something like that. Yeah, 5 per minute. Oh man, makes sense. Okay, and I don't have to know whether they can keep it up or not. It's just instantaneous speed. Yeah. 60 seconds over 1 minute. So I can get revolutions per minute. Okay? Anybody still need that? Okay. Whoop. Show one more. I'm sure my video people can figure it out. Come here. Well, I'll pause and let you